Okay, in this video, I'm going to continue with our discussions of the calculus test number one practice, and this time we're taking a look at the calculator permitted questions. Well, in example number one, we're being asked to evaluate the limit, and we do have a calculator available to us, but I don't think it's necessary this time because anytime that I try to evaluate a limit, one of the first things that I consider are algebraic methods for doing so. So can we simplify them using any sort of factoring or other techniques that we've talked about in class. And in this particular case, factoring works just as well as it did in the no calc portion. So I would argue factoring it and then directly substituting towards the end would be the approach to go. Just remember that along the way, as we're simplifying using algebra, it's the limits that are equal to one another, and it's not until direct substitution that we can drop that limit notation. That's when the limit value or the limit component of the expression actually can be removed. Problem number two, we see the same thing. While we can't directly substitute the number one at the beginning, simple factoring shows that the factor can be removed. The x minus 1 binomial factor can be removed, and then at that point we can apply direct substitution and continue finding the limit. For number three, we are looking for the limit as x approaches -2 from the right. And I think I just recognized an error here. Well, let me just explain what my thoughts were, and then we'll try to fix this in this video here. Since we are approaching -2 from the right, what I should have done is either jotted this down or made a better mental note. If this is -2 on the number line, -2 from the right would be approaching from over here. And while we've got -1 and we're approaching -2, we should be thinking about numbers -1.9, -1.99, -1.999, and so on. These are the numbers that are getting closer to -2 as we move from right to the left. So we're going to need to fix that table here. Additionally, since we're coming from the right, we are concerning ourselves with x values that are bigger than 2. And so in my notes, I had highlighted that first part of the piecewise function, but it really should have been this one. When x values are greater than -2, we're talking about this position over here. Anything to the right of -2 is greater than -2. And anytime that x is greater than -2, we're using this line of our piecewise function. So a more appropriate table might look something like this. So again, we're choosing x values that are on the right side of -2, and we're getting closer and closer to -2 as we move across here. I'm going to open up a calculator now since I have it available to me, and I'm going to evaluate this function at each of these numbers. Here's that calculator, and we need 2 times x, which our first x value is -1.9, 2 times x plus 1, and at the number x value of -1.9, our y result is -2.8. If I go to the calculator again and investigate what happens just a little bit closer to -2, that's pretty easy to do. We can copy the equation down and rerun it, and now we see -2.98, and I bet you can already discover the pattern. But let's go ahead and check it just to be safe. In case we encounter any trig functions that oscillate, it would be a good idea to check more than just one or two of these values as we approach our limit value, our limit location. And the pattern's going to hold true if this is what you were thinking. This is also good evidence for me as I'm scoring your test that you truly understand what's happening here. And so as x is tending towards -2 from the right, f of x, the y values, the function results, are tending towards -3. So we're going to say that this answer is -3 instead of -2. And it's not because this table was wrong. Well, it sort of was because we used the wrong x values. But really the biggest problem here is that when I started my answer key, I had focused on the wrong portion of the piecewise function. So hopefully you understand and learn from my mistake and can see this correctly when you see your problem similar to this on the test this week. For number 4, I just used a graphing tool on the TI Inspire, and I investigated it as x approached -1 from the right. And as we approach -1 on the x-axis from the right side, we see that this function is tending towards 2, and that's why I went with that solution. The Inspire can graph these absolute functions pretty easily, and I think the TI-84s can do that as well. But since we use Inspires mostly in this class, and I like to reference them, I'll show you how to build that into a graphs page. So I'm just going to press Control and then this document key, because that's going to add a page. And we want a graphs page to this document. And the function, let's build a fraction first, with a numerator of 2x plus 2. Press the down arrow to jump down below, and this is where our absolute value comes in. We want the absolute value of x plus 1. Now the easiest way to enter this that I know is just to simply type ABS. Otherwise you're going to have to go looking for this command, in all kinds of different menus and libraries. If you remember that ABS stands for absolute value, you'll notice that as you type that in, the letters switched from italic to regular font. That means that it's a built-in function for the system, and anything that we write inside of the parentheses here will be executed as an absolute value function. Now what's interesting about this is that in the Inspire, if you type something like SQRT, I believe that's the shortcut, you can get the square root function to pop up. And that's particularly helpful, those and other functions, when you're using the emulator on your computer, which again is free for download for Butler Tech students. You can have this emulator that I'm using on my screen and use your keyboard to execute a lot of functions, and that could save some time. So anyway, I just tap the enter key here and the graph is displayed, and this is the same one that you saw as a screenshot on my paper here. I think it would be a good idea during the test to go ahead and sketch this graph. So if you had shown me an XY axis with a portion of the graph indicated with the absolute value bars here, the steps I should say, I think that would be a pretty good indicator of your understanding of this particular function. Now, technically there are open circles there. The second one should not be closed, and that would be a bit more accurate. But when it comes to the limit as we're approaching from the right-hand side, it doesn't matter whether that's an open or a closed circle. So for the last two examples, we're being asked to find the slope of a function at the given value. Now that's going to be required of these questions. The bonus would be to find the equation of the tangent line at that point. And we'll talk about that probably in another video. If it's not immediately clear here, I'll run through an example or two on another video. Well, to find the slope of the function, we were using the difference quotient. And the formula for the difference quotient that I'm a particular fan of is this one, where the difference quotient, let me use a different color here. The difference quotient allows us to find the slope of an instantaneous rate of change, or a tangent line. And that's simply equal to the limit as h approaches 0 of the function evaluated at x plus that h value minus f of x divided by h. This is simply a modified form of our slope function, and we're picking 2 points that are very close to one another, only separated by a horizontal distance of h. And ideally, that horizontal distance would be nothing. We can't do that with traditional algebra because that would mean dividing by 0. So we institute the limit as h approaches 0 of this definition. When h is 0 and we provide an x coordinate, then we can find the slope of the line at that particular point. So in this case, we have a function that's y equal 2x squared minus 2. And with this equation, we would then execute the simplification of the difference quotient. So here is 2x squared minus 2, but instead of x, we're using x plus h because that's how the definition was described. Here's the f of x component. I expanded and distributed and then ultimately looked for terms that would cancel in the numerator here. Several did. I factored in the numerator the h value from the remaining components, 1, 2. And with the h values factored from here, I was able to cancel the h in the numerator and the denominator. Now, along the left-hand side, pay close attention here that I said that the slope, m, is equal to the limit of this expression, and that's equal to the limit of this expression, which is equal to the limit of this expression, which is equal to the limit of this expression. It's not until the very end that we were able to directly substitute an h value of 0, and when we were able to evaluate or directly substitute an h value of 0, that's when we did, and that's when we dropped the limit notation. So we ultimately ended up with an equation for x, and that says that this is the formula used to find the slope at any given point. Now our instructions up here said to find that slope when x was equal to -1, and I just took it upon myself to put this red dot here. When x is equal to -1, we're talking about this coordinate. And if we were looking at this coordinate, it kind of looks like there's a negative slope there. So let's see if we can calculate what that negative slope should be. Well, using this formula, when x is equal to -1, the difference quotient says that the slope of the tangent line at that point is equal to -4. And if I draw a line through this point with a slope of -4, that's the green line that I've shown here, that certainly looks like a line tangent to the blue curve, and I feel fairly confident with that. The bonus would be to establish the linear equation through this point in slope-intercept form. And if you didn't notice it initially, I'll just quickly mention it now. I started with the point slope formula in this first line, and I simplified the point slope formula into the slope-intercept form. And this would be the equation for the linear equation, this green line, through this red dot. In this last example, the equation looks a little bit more challenging because of the fraction bar, but as long as you can recognize that this term here could really be written as -1/2 x squared instead of x squared divided by 2, if you think of it as written that way, then simplifying the difference quotient becomes a little bit more manageable. It does look a little bit scary at first when you're substituting the x plus h twice in the expression, but again, with practice and strong algebra skills, you should be able to handle it. In class, I elected to simplify f of x plus h off to the side. I would always do that work over here and then bring it into the difference quotient. For this answer key, well, I just didn't do that. I'll leave that up to you, whether you want to do that simplification outside of the fraction or inside of the fraction. It won't make a difference to me. Now, as terms cancel, combine and equal or add to equal 0, we're again left with a collection of terms that contain a common h. With that common h factored out and the remaining terms indicated in the numerator, we can cancel the h from the numerator and the denominator. They factor to 1, and we've got an expression here where the limit as h approaches 0 is this expression. With direct substitution, we're left with -x minus 2. So when we need to find the slope at x equals 0, when x is equal to 0, we have a coordinate right here. That, again, looks like a negative slope, not quite as steep as what we saw in the last example. And when I substitute 0 in place of x, we see that the slope is indeed -2 and not as steep as this example was back here. With the point slope formula, we had a coordinate at 0, -2. We had a slope identified of -2 from the difference quotient, and as we simplify, we see the equation is -2x minus 2. So I hope that this pair of videos can help you better understand questions that showed up on the practice test. If you have further concerns or questions, please send me a message through Schoology or email me directly, and I'll try to respond to that and post videos to our course online. Thanks for watching.